Warning, system anomaly detected. You are now accessing kernel panic logs, a real-time terminal for learning in public. This is your audio study guide. Concepts loading. Execute.
So think about a medical x-ray for a second. When a doctor looks at an x-ray of your arm, they're looking at this highly compressed, totally unique snapshot of your internal state.
Right, at that specific moment in time.
Exactly. They can uniquely identify your bone structure from that one image. But, this is the crucial part, no one can take that two-dimensional x-ray and mathematically reconstruct the living, breathing human being from it.
No, of course not. It's a completely one-way transformation.
Right. And in the digital world, every password database, every file you download, and every Git commit you make relies on an algorithm that does exactly that. We call it a cryptographic hash function.
Yeah, and the funny thing is, most IT practitioners rely on these systems daily, but they just treat them as complete black boxes.
Oh, totally. Data goes in, a random string of characters comes out, and nobody really asks what actually happened inside.
Well, that changes today. Since you're joining us for this deep dive into the kernel panic log study guide, we're assuming you already have a solid working knowledge from our previous discussions on cryptography fundamentals.
Right, like from episode 1 and 2.
Yeah, exactly.
Yeah.
You know the mechanics of symmetric encryption, you understand block ciphers like AES, and you grasp the basic principles of confusion and diffusion.
So we're not going to re-explain all of that from scratch.
No, we are going to build directly on that foundation to really tear apart the inner architecture of cryptographic hash functions. We'll look at the underlying math that causes them to break and explore how modern architectures fix those structural flaws.
Okay, let's unpack this because we need to draw a hard line right out of the gate. People constantly confuse hashing with encryption.
Oh, all the time. It's probably the most common misconception.
Right. But if encryption is like a two-way street where a secret key lets you drive the ciphertext back to the original plaintext, hashing is a one-way drop.
A one-way drop. I like that.
Yeah. Once the data goes into that algorithmic wood chipper, there is absolutely no key that can mathematically put the original message back together. It's not just practically difficult, it's a one-way mathematical reality.
And that distinction is really the bedrock of everything we're covering today. A hash function has a very specific mandate. It takes an input of an arbitrary length. Like anything, literally anything. It could be a single text document, or it could be a terabyte of server backups. It takes that arbitrary input and it compresses it into a fixed length output, which we call a digest.
Okay.
Furthermore, it is purely deterministic, meaning if you feed it the exact same terabyte of data 1 trillion times, it will yield the exact same output digest 1 trillion times.
And it does this while maintaining something called the avalanche effect, right?
Yes, the avalanche effect is critical.
Because if I have, say, a 1 gigabyte video file, and I change a single pixel in a single frame, like literally flipping one bit of data from a 0 to a 1, the new hash won't just be slightly different.
No, it won't just change by one character.
It'll be utterly unrecognizable from the first hash. Every single bit of the output has a roughly 50% chance of flipping, just because of that one microscopic change in the input.
Exactly. And the mechanics of how that happens rely heavily on those confusion and diffusion principles you already know. These algorithms are designed with extremely dense internal loops of logical operations.
So we're talking about nonlinear functions, modular additions, bitwise XORs.
Right, all stacked on top of each other. So when you flip that single input bit, that change cascades through the dense web of operations, multiplying its influence across the entire data block until the final output looks completely uncorrelated to the original.
Wow.
But this core mandate, taking infinite inputs and compressing them into a fixed number of outputs, it creates an unavoidable mathematical tension.
Right, because of the pigeonhole principle. Yeah. If we're squishing infinitely many possible file sizes and combinations into a rigidly fixed number of bits, say 256-bit output, aren't collisions mathematically inevitable? I mean, if you have more pigeons than pigeonholes, two pigeons are eventually going to have to share a hole.
They are. Collisions are a mathematical certainty. Two different files that produce the exact same hash absolutely do exist out there.
Wait, really?
Oh yeah. The entire premise of a secure cryptographic hash function isn't that collisions don't exist, it's that they must be computationally infeasible to find.
Okay, that makes sense.
So to evaluate if an algorithm is actually secure, cryptographers test it against 3 highly specific security properties. If it fails any of the 3, the algorithm is considered broken.
Let's lay those out because I know they sound similar, but they have very different implications for an attacker.
Sure. So the first property is pre-image resistance. This means that given a specific hash output, it is computationally infeasible to find its original input.
So if a database leaks a list of hashed passwords, an attacker shouldn't be able to just reverse engineer the passwords from the hashes alone.
Exactly. You can't work backward. The second property is second pre-image resistance. This applies when an attacker already has both a specific file and its resulting hash.
Okay, so they have the source and the digest.
Right. The algorithm must make it impossible for the attacker to find a totally different file that produces that exact same hash.
So if I have a legally binding signed contract and its hash, second pre-image resistance ensures an attacker can't maliciously swap in a modified contract that just coincidentally produces the identical signature.
That is the exact real-world application, yes. And then the third property is collision resistance. This is the broadest and honestly the most difficult to maintain.
Why is that?
Well, collision resistance means you cannot find any 2 random inputs that hash the same value. The attacker isn't given a target hash to match, they just have to find any 2 pieces of data in the universe that happen to collide.
Wait, why is collision resistance considered the hardest property to maintain? I mean, finding any 2 inputs in a universe of infinite inputs still seems like looking for 2 identical grains of sand on a beach.
Yeah, human intuition is notoriously terrible at grasping probability. If we look at the math behind pair matching, finding any 2 inputs that collide is drastically easier than matching a specific input.
Okay.
Cryptographers call the mathematical phenomenon that exploits this the birthday attack, based on the birthday paradox.
Oh, right, the room full of people analogy.
Exactly.
If you ask a random person how many people you need in a room to have a 50% chance that 2 of them shared the exact same birthday, they usually guess a huge number.
Yeah.
Like half of 365.
But the actual mathematical answer is just 23 people.
Just 23. It always blows my mind.
But the math works that way because you aren't comparing 23 people to one specific birthday leg. You aren't checking if anyone is born on January 1st.
Right.
You are comparing every person to every other person in the room. The number of possible pairs grows exponentially with every new person who walks in.
Wow, okay.
So when cryptographers apply this probability model to hash functions, it generates what we call the square root rule. A hash function with an n-bit output is vulnerable to a birthday attack in roughly 2 to the power of n divided by 2 operations.
So the birthday paradox effectively cuts the perceived security of the hash's bit length exactly in half.
It does, and that is a devastating reality for older algorithms.
So let's look at the practical implications of that. MD5 is a classic algorithm, right? With a 128-bit output.
Yes, and according to the square root rule, finding a collision in MD5 doesn't take 2 to the 128th power operations. It takes roughly 2 to the 64th power.
And SHA-1.
SHA-1 has a 160-bit output, so finding a collision takes about 2 to the 80th operations.
Okay, let me play devil's advocate for a second here. 2 to the 64th power operations is what, about 18 quintillion hashes?
Roughly, yeah.
To a normal person, that still sounds like an impossibly massive number. Why is 18 quintillion operations considered dangerously short in modern cryptography?
Because hash functions, by their very nature, are designed to be fast and efficient. They don't require the complex, time-consuming math of public key cryptography.
Oh, right. They're meant to be quick.
Extremely quick. An attacker can compute them incredibly fast. Today, a distributed network of GPUs, or even just a rented cluster of cloud computing instances, can compute billions of hashes per second.
Jeez.
So brute forcing 2 to the 64th operations isn't science fiction anymore. It's something a well-funded research group or a nation-state can literally execute over a weekend.
Okay, that makes sense. Yeah. We know the mathematical limit of these outputs now, but let's look under the hood. How do these algorithms actually process a massive, say, 10 gigabyte video file into those final 128 or 160 bits? They obviously don't just swallow a gigabyte of data into the CPU all at once.
No. They process it in chunks using a very specific architectural framework called the Merkle-Damgard Construction.
Oh, well, Damgard.
Right. For decades, this was the absolute gold standard for hash design. MD5, SHA-1, and even our modern SHA-2 all share this exact same lineage.
Oh, interesting.
The Merkle-Damgard construction works by taking that arbitrary length input and breaking it down into fixed size blocks, typically 512 bits at a time.
But files in the real world rarely divide perfectly into clean 512-bit chunks, right? There's almost always a remainder.
Which is exactly why the algorithm relies on length padding.
Okay, how does that work?
Before any hashing begins, the algorithm looks at the final incomplete block of data. It appends a single 1 bit to act as a separator, fills the rest of the empty space with zeros, and then, and this is the critical security feature, it encodes the exact length of the original unpadded message at the very end of the block.
Oh, I see. By appending the exact length, the algorithm ensures that an attacker can't just secretly add a bunch of zeros to the end of a short file to make it mathematically collide with a longer file.
Exactly. It locks in the original size.
Okay, so the data is perfectly sliced into blocks and padded. How does the actual compression work?
The architecture uses a compression function that loops over the data. It starts with an initialization vector, which is just a fixed, standardized starting state.
Right.
The algorithm compresses that starting state together with the first 512-bit block of data. The output of that mathematical compression becomes the starting state for the next block of data.
Oh, I get it.
It loops this process over and over until the final padded block is processed. The output of that very last compression is your final hash digest.
So it's essentially an assembly line.
That's a great way to picture it, yeah.
You feed a chunk of raw material into the machine, it grinds it up, and hands the resulting glob to the next machine along with the next chunk of raw material. It just keeps passing the state forward.
Yes, but that assembly line structure, while highly efficient, harbors a fatal structural flaw. Because the final hash digest you see is literally just the internal state of the algorithm after processing the final block, an attacker can exploit it. If an attacker knows the final hash of a secret message, they can load that hash into their own local machine, use it as the new starting state, and simply feed more data blocks into the algorithm.
Wait, seriously? So they don't even need to know the original secret message?
Nope, not at all.
They can just take the final hash, glue their own malicious data to the end of it, and the algorithm will output a perfectly valid hash for the newly extended message.
Yes, that is known as a length extension attack, and it is the native structural weakness of the Merkle-Damgard construction. Any algorithm built on this assembly line framework is theoretically vulnerable to it.
Wow, that seems like a massive architectural oversight. When you combine that structural flaw with the dangerously short bit lengths we talked about earlier, it feels like a recipe for disaster.
It definitely was.
Let's trace how this actually played out in the real world with the fall of MD5 and SHA-1.
Sure, so MD5 was created by Ron Rivest in 1992. It had a 128-bit output and became the absolute standard for a decade. But by 2004, a team of Chinese cryptanalysts, led by Xiaoyun Wang, dropped a bombshell on the security community.
Did they brute force it using the square root rule?
No, they didn't just brute force the algorithm. They demonstrated a method for finding collisions in MD5 that bypassed the brute force requirement entirely. They found mathematical shortcuts in the internal loops.
Oh, wow.
MD5 went from being theoretically vulnerable to being trivially broken. Today, you can generate an MD5 collision on a standard consumer laptop in a matter of seconds. It should never be used for security purposes.
And SHA-1, which had a slightly longer output, wasn't far behind, right?
Right. SHA-1 was designed by the NSA and standardized in 1993. Because it had a 160-bit output, the math held on a bit longer. But the watershed moment happened in 2017.
What happened then?
Google, working with researchers from CWI Amsterdam, devoted tremendous computational resources to execute what they call the shattered attack.
Shattered. Nice.
Yeah. They successfully generated a collision, producing two distinct PDF files with completely different visible contents that possessed the exact same SHA-1 hash. Following that proof of concept, NIST formally deprecated SHA-1.
You know, I really want to highlight the real-world danger of what a collision actually means here, because it's not just about messing with PDFs.
Oh, absolutely not.
If a bad actor can reliably generate a collision in MD5 or SHA-1, they can write a malicious executable like a stealthy ransomware payload and manipulate the garbage data inside the file until it mathematically shares the exact same hash as a legitimate Windows update or a trusted software patch.
Exactly.
If an IT system relies purely on MD5 or SHA-1 to verify the integrity of that download, The system will look at the hash, see a match, and blindly execute the malware.
That is the nightmare scenario, and it really highlights why practitioners must understand this lineage. We sit here and state that MD5 and SHA-1 are mathematically broken, but the terrifying reality in the field is that they still haunt legacy systems.
Yeah, everywhere.
You will routinely encounter old network routers, embedded medical devices, and aging databases that still rely on MD5 hashes. You have to know the underlying mechanics of these breaks so you can accurately assess the risk and prioritize migrating away from them.
So with the public execution of MD5 and SHA-1, the industry desperately needed a new workhorse. And that brings us to SHA-2.
Yes. SHA-2 is the dominant standard running the internet today. When practitioners reference SHA-2, they're primarily talking about its two main variants, SHA-256 and SHA-512, which are named for their output bit lengths.
And it is genuinely ubiquitous. Like every time you connect to a secure website, SHA-256 is securing that TLS certificate. It's the cryptographic puzzle that entire server farms are solving for Bitcoin mining. It verifies our software code signing and securely hashes modern passwords.
It's everywhere.
But knowing what we just discussed about the underlying architecture, how different is SHA-2 from the algorithms that failed?
Structurally, it is not different.
Wait, really?
Yeah, SHA-2 relies on the exact same Merkle-Damgard assembly line construction that MD5 and SHA-1 used. Oh, wow.
The designers simply gave it a significantly larger internal state, introduced much more complex bitwise operations, and added more rounds of compression. The larger 256-bit output completely neutralizes the birthday attack, making brute force collisions practically impossible with modern technology.
But I have to point out the elephant in the room here. If SHA-2 uses the Merkle-Damgard assembly line, doesn't it still possess the length extension vulnerability? I mean, just making the math harder and the output longer doesn't change the fact that the final hash is just the internal state of the machine.
You are identifying the exact concern that kept cryptographers awake at night. You are completely correct.
Okay.
While SHA-2 remains completely unbroken in terms of collision resistance, nobody has ever found a collision in SHA-256. The length extension vulnerability is still structurally present.
That's terrifying. The security community realized that simply adding more bits to a flawed assembly line wasn't a permanent solution. If a mathematical shortcut was found for SHA-2, the entire digital economy would be at risk. They needed a backup plan, built from the ground up on a totally different architectural philosophy.
Which initiated the search for SHA-3.
Exactly. Between 2007 and 2012, NIST ran a massive public competition to find the next generation of cryptographic hashing. The winner was an algorithm named Keccak, which was formally standardized as SHA-3.
Keccak.
Yep. And it is crucial to understand that SHA-3 is not intended as a mandatory replacement for SHA-2.
Because SHA-2 isn't broken yet.
Exactly. SHA-2 is still computationally secure. Rather, SHA-3 is an alternative designed with completely different structural properties to act as a hedge. If someone breaks the math behind SHA-2 tomorrow, we have a fundamentally different pre-standardized backup ready to deploy. Practical variants like SHA-256 and SHA-512 are available right now.
And the architecture Keccak uses abandons the assembly line entirely, right?
Mm-hmm.
It uses something called the sponge construction.
Yes.
How does that fundamentally alter the way data is processed?
The Keccak sponge construction processes data in two distinct continuous phases, the absorb phase and the squeeze phase. Instead of compressing a block of data and passing the entire state forward to the next block, the sponge maintains a massive, persistent internal state, 1600 bits in the case of SHA-3.
1600 bits, wow.
During the absorb phase, the blocks of your input message are mathematically XORed into only the first part of this internal state, a section called the byte rate. The data is then subjected to complex mathematical mixing.
Let me see if I can visualize this using the actual name. It's literally like a kitchen sponge.
Sure.
During the absorb phase, you're soaking up the water, the data, into the outer layers of the sponge. You squeeze and mix it internally to distribute everything. But what happens to the rest of those 1600 bits that weren't directly touched by the input message?
That untouched section is the genius of the architecture. The remaining trailing bits of the internal state are called the capacity. The input message never directly interacts with the capacity bits. And later, during the squeeze phase, when the algorithm finally extracts the output digest, it only wrings that output from the byte rate section.
Oh, I see the implication. Because the attacker can never see the capacity bits in the final output, and they can never directly manipulate the capacity bits during the input, they're totally blind to a massive portion of the algorithm's internal state.
Precisely. And if they cannot see or reconstruct the full internal state, they cannot perform a link extension attack.
That is brilliant.
The sponge construction effectively immunizes SHA-3 against the fundamental flaw that plagued every previous generation. It is a massive leap forward in cryptographic design.
Yeah, it really is.
But understanding how to generate a secure hash using SHA-2 or SHA-3 is only the foundation. In the field, we must also understand how to use these hashes to actively authenticate data as it travels across hostile networks.
Right, because a hash alone only proves data integrity, not authenticity. If I send you a sensitive file and it's SHA-256 hash across the internet, a man-in-the-middle attacker could just intercept the file, alter the contents, generate a brand new SHA-256 hash for their malicious version, and send both on to you.
And you would have no idea.
Right. You'd calculate the hash on your end, see that it matches the file, and falsely believe everything is fine. A standard hash doesn't prove who sent it.
Right. To solve the authentication problem, we combine hashing with shared secrets to create a message authentication code, MAC. By introducing a secret key into the hash function, we create a keyed hash. Only someone possessing the secret key can generate the correct hash for the file.
Well, wait, we just spent the last 10 minutes talking about the length extension vulnerabilities in SHA-2. If I just glue a secret password to the front of a file and hash them together, an attacker could use the length extension flaw to append data and forge a valid MEC without ever knowing my secret password.
They could, which is exactly why you can never just concatenate a key and a message.
Okay, so what do we do?
To safely combine a secret key with a hash function, the industry relies on a standardized construction called HMAC, or Hash-Based Message Authentication Code. HMAC bypasses the structural weaknesses of Merkle-Damgard by using a clever system of nested hashing.
Nested hashing?
Right. It takes the shared secret key and mathematically mixes it with two different padding schemes, an inner pad called IPAD and an outer pad called OPAD.
Let's walk through the mechanics of that nested process. How does it actually work?
First, the algorithm hashes the original message together with the key that has been modified by the inner pad.
Okay.
That first hashing operation secures the data itself. Then, the algorithm takes the resulting digest from that first operation and it hashes it a second time. But this time, it combines that intermediate digest with the key modified by the outer pad.
So it's wrapping the message in two distinct layers of keyed cryptography. By hashing the output of the first hash, the algorithm effectively seals off the internal state. Even if the underlying algorithm is SHA-2 and inherently vulnerable to length extension, the double wrap of the HMAC construction makes it mathematically impossible for an attacker to extend the message and manipulate the state.
That nested security is why HMAC SHA-256 is the absolute standard for API authentication, secure web tokens, and modern session management today. It guarantees both the integrity of the data and the authenticity of the sender.
That's incredibly elegant.
It is, but it does have one fundamental limitation we need to acknowledge. HMAC relies entirely on a pre-shared symmetric key.
Right.
Both the sender and the receiver must possess the exact same secret. It proves the message came from someone holding the key, but it doesn't allow for public verification. Anyone who can verify an HMAC can also forge one because they possess the secret.
Oh, I see.
If you want true non-repudiation, where anyone can verify a signature but only one person can create it, you need asymmetric digital signatures, which we will dive into in the future.
You know, it's incredible to step back and look at this journey. We've gone from the conceptual basics of one-way compression, walked through the exponential math of the birthday paradox, traced the evolution from the Merkle-Damgard assembly line to the Keccak sponge, and finally secured our data in transit with the nested layers of HMAC. Hash functions truly are the connective tissue of modern cryptography. Every secure connection, every validated packet, and every authenticated system relies entirely on the mathematical machines we dissected today.
They really do. But our discussion of HMAC leaves us with a critical, unresolved puzzle for you to ponder.
What's that?
We just established that HMAC secures a message using a shared symmetric key. But if you and I are on opposite sides of the world, communicating over a monitored, hostile internet, How do we securely share that secret key with each other in the first place without the attacker just intercepting it?
Oh, right. That is the key distribution problem. You can't securely mail a padlock to someone if the key gets stolen in transit.
Exactly. It's the exact puzzle that public key cryptography and our next deep dive is designed to solve.
Perfect. Remember that medical x-ray from the beginning. These hash algorithms aren't magic. They are precise mathematical tools with real physical limits. Once you stop treating them like black boxes, you realize you have the power to actually lift the hood, see exactly how the engine runs, and understand the limits of the trust you place in them. Thanks for joining us on this deep dive. See you in the next one.
End of log. The full flashcard deck is linked below. It's free. It's how I study. If this helped, subscribe. More logs incoming. Kernel panic logs out.